Hi, I'm Todd Sherman from Idaho State University, and I'll be presenting on my PhD research developing a new series of high entropy carbides for nuclear applications. Imagine a large nuclear power plant that could operate for more than 120 years. Imagine if this plant did not have to deal with reactor vessel neutron embrittlement or even any significant wear on any vessel internals components while operating at temperatures around 1000 degrees Celsius. That is the possibility of today's research for tomorrow's reactor and the premise of my PhD research. I'm developing and characterizing a new series of high performance materials for tomorrow's advanced reactors. My project is endeavoring to marry the performance of newly developed high entropy alloys along with the radiation resistance and stability of carbides in a series of new high entropy carbides. First, in my project, I've started off by mixing common high quality industrial carbides together, then rapidly sintering them together under extremely high temperatures and pressures in a spark plasma sintering furnace. Next, the samples have been characterized to determine their respective properties as newly formed materials. The atomic crystalline structures, lattice constants, and phases have been identified by X-ray diffraction scanning. Several iterations of the synthesis process have been carried out to determine the optimum sintering conditions to produce the best single-phase materials with the highest relative densities. Following the initial characterization, the thermal and mechanical properties of these new materials have been measured through thermal diffusivity and indentation hardness testing. To determine the irradiation performance of these materials, they are being irradiated via heavy ion bombardment. Several samples are being irradiated up to nearly 100 displacements per atom to determine their responses across a wide range of irradiation damage levels. Following the ion irradiations, my samples will be thoroughly examined to identify any volumetric swelling, atomic morphization, and radiation-induced segregation brought on from the irradiations. These new high entropy carbides can potentially have many wonderful applications in the advanced nuclear reactors. Their relatively high densities and heavy metal contents make them great for shielding against gamma rays, while their high carbon content would serve as a neutron shield and reflector. Past research has demonstrated the superior stability of many different carbides at very high radiation levels. I believe that the radiation resistance of these new high entropy carbides will be even more enhanced. High entropy carbides could serve as reactor vessel shielding materials, greatly reducing the fast neutron fluences and therefore preserving the life of the reactor vessels. Carbides also have very high wear resistance, making them ideal for a wide range of applications to resist both mechanical wear and flow-induced corrosion and wear. Carbides are proven to be very chemically stable and corrosion resistant, even at very high temperatures, making them suitable for many different potential reactor coolants at all temperature ranges. I am very excited about our nuclear future and hoping that my research can contribute to making tomorrow's nuclear reactors perform safer, better, and longer. Thank you.